Committee voting under uncertainty is a complex problem that has garnered significant attention in recent years. In this context, approval-based voting systems have emerged as a promising approach. However, the challenge lies in selecting a target number of candidates based on voters' uncertain approval preferences. To address this issue, the paper proposes a novel framework for approval-based committee voting under uncertainty. The authors model voters' uncertain approval preferences using a probabilistic approach, where each voter has a probability distribution over the set of candidates. The probability distribution represents the voters' uncertainty about their approval preferences. The paper introduces a new scoring rule, called the Expected Approval Score, EAS, which aggregates voters' uncertain approval preferences to determine the winning committee. The EAS rule takes into account the probability distributions of voters' approval preferences and computes the expected approval score for each candidate. The authors prove that the EAS rule satisfies several desirable properties, including Pareto efficiency, symmetry, and resistance to manipulation. Furthermore, they show that the EAS rule is computationally efficient and can be approximated using a randomized algorithm. The paper also presents an empirical analysis of the EAS rule, demonstrating its effectiveness in selecting a diverse set of candidates that accurately reflect the voters' uncertain approval preferences. The results demonstrate that the EAS rule outperforms existing voting rules in terms of social welfare and voter satisfaction. A key contribution of the paper is the introduction of a new concept called uncertain approval diversity, UAD, which measures the diversity of the winning committee in terms of voters' uncertain approval preferences. The authors show that the EAS rule maximizes UAD, ensuring that the selected committee is representative of the diverse opinions and preferences of the voters. The paper concludes by highlighting the limitations of the proposed framework and outlining avenues for future research. Specifically, the authors note that the EAS rule assumes that voters' uncertain approval preferences are independent, which may not always be the case in practice. Future work should focus on relaxing this assumption and exploring more sophisticated models of voter uncertainty. Overall, the paper contributes to the growing body of research on committee voting under uncertainty, providing a novel framework for approval-based voting that takes into account voters' uncertain approval preferences. Voters' uncertain approval preferences pose a significant challenge in social choice theory, particularly in situations where voters may have incomplete or uncertain information about candidates or alternatives. This paper introduces a framework to address such problems, leveraging techniques from decision theory and game theory to model voters' uncertain approval preferences. The researchers employ a probabilistic approach, representing voters' preferences as probability distributions over approval sets. They define a novel concept, the approval probability distribution, which captures the likelihood of a voter approving a particular alternative. This representation enables the analysis of voting rules under uncertainty, facilitating the evaluation of their performance in the face of incomplete information. A key contribution of the paper is the development of a new voting rule, the Probabilistic Approval Voting (PAV) rule. PAV incorporates the approval probability distributions to determine the winner, taking into account the uncertainty in voters' preferences. The authors demonstrate that PAV satisfies desirable properties, such as Pareto efficiency and strategy-proofness, under certain conditions. The researchers also investigate the computational complexity of PAV, showing that it can be implemented efficiently using a polynomial time algorithm. Additionally, they provide an axiomatic characterization of PAV, establishing its uniqueness among voting rules that satisfy specific axioms. The paper concludes by discussing limitations and avenues for future research, including the extension of PAV to more complex preference models and the investigation of its performance in real-world scenarios. Approval-based committee voting under uncertainty is a complex problem, particularly when considering justified representation, junior, and extended justified representation, EJR. A comprehensive summary of results is presented, showcasing the complexity of various problems related to these axiomatic properties. The complexity of several problems is summarized, including checking whether a committee is possibly or necessarily junior or EJR, computing the committee that maximizes the probability of satisfying junior or EJR, and determining the existence of a committee that satisfies junior or EJR. Notably, most of these problems are NP-complete or CONP-complete, except for special cases where the input information is restricted or the approval profiles are of size 1. In comparison to previous research, the authors' approach differs significantly. They highlight the work of Imber et al., which proposed models of incomplete information but did not examine problems such as maximizing the probability of satisfying an axiomatic property like junior. The authors also discuss the work of Halpern et al., which focused on query complexity and approximating junior and EJR for selecting comments based on agreements and disagreements. Additionally, the authors mention related work in the context of matching and allocations, including the study of computing stable matchings under uncertain preferences. This research contributes to the understanding of the complexity of approval-based committee voting under uncertainty, emphasizing the challenges of achieving junior and EJR in such settings. In the context of approval-based committee voting, joint probability models are employed to capture scenarios where voters may be uncertain about their approval ballots. 3 distinct uncertainty models are introduced: the joint probability model, the lottery model, and the candidate probability model. The joint probability model assigns a probability distribution over approval profiles, where each profile has a positive probability. In contrast, the lottery model assigns a probability distribution to each voter's approval sets, assuming independence among voters. The candidate probability model assumes that each voter approves each candidate independently with a certain probability. These models are crucial in evaluating the performance of voting rules under uncertainty. The authors examine various proportional representation axioms, including justified representation, junior, proportional justified representation, PJR, and extended justified representation, EJR. These axioms aim to ensure that the winning committee reflects the diverse preferences of the electorate. Junior requires that a voter is represented if they approve a candidate who is not already represented. PJR strengthens this requirement, demanding that the number of representatives for each group is proportional to the number of voters in that group. EJR further refines this concept, considering the joint probability distributions over approval profiles. By analyzing these axioms in the context of joint probability models, the authors provide a deeper understanding of the trade-offs between different voting rules and the importance of considering uncertainty in the voting process. The results of this analysis have significant implications for the design of voting systems, highlighting the need for careful consideration of the underlying uncertainty models and their impact on the representation of diverse voter preferences. In approval-based committee voting under uncertainty, the three-valued approval, 3VA, model allows voters to specify approved, disapproved, and uncertain candidates, represented as pi, C element of 0, 0.5, 1, where 0 denotes disapproval, 1 indicates approval, and 0.5 represents unknown. This model builds upon the joint probability and lottery models, which have been applied to two-sided stable matching and assignment problems. The 3VA model has been specifically studied in the context of the ABC voting system. A direct generalization of the 3VA model is the candidate probability model, which assumes independent pi, Cs. A crucial concept in these uncertainty models is a plausible approval profile, defined as an approval profile that can occur with positive probability under any uncertainty model. Proposition 1 establishes a unique joint probability model representation for P, providing a foundational framework for understanding approval-based committee voting under uncertainty. This representation enables the analysis of voting outcomes under different uncertainty models, shedding light on the complexities of approval-based committee voting. Computational problems related to necessary and possible justified representation, junior, are examined in this section. Necessary junior involves two primary computational problems: deciding whether a given committee W satisfies junior with probability 1, and determining if there exists a committee W that satisfies junior with probability 1. The authors also investigate the JR probability problem, which computes the probability that a given committee W satisfies junior. Furthermore, they explore the max JR problem, which aims to find a committee W with the highest probability of satisfying junior. Shifting focus to possible junior, the authors demonstrate that exists POS JR has a trivial yes answer for all probability models, as a committee W satisfying junior with non-zero probability always exists. In contrast, is POS JR. The problem of deciding whether a given committee W satisfies junior with non-zero probability exhibits varying complexities across different probability models. Specifically, is POS JR is in polynomial time for the joint probability, 3VA, and candidate probability models. However, under the lottery model, is POS JR is NP complete, even when each voter assigns positive probability to at most 3 approval sets and k equals n, 2. To prove the NP hardness of is POS JR under the lottery model, the authors employ a reduction from 3 SAT, a well-known NP complete problem. They construct an instance I of is POS JR by creating one voter per clause in a 3CNF formula, with each voter assigning positive probability to 3 approval sets corresponding to literals in their clause. Dummy candidates are introduced, and a committee W is created that includes these dummy candidates. The authors show that I has a solution if and only if the original 3CNF formula I is satisfiable, thereby proving the NP hardness of is POS JR under the lottery model. The authors establish a polynomial time solvable algorithm for determining whether a given committee W satisfies the justified representation, junior, property with probability 1 in the lottery model. This result is achieved through a reduction from the 3 SAT problem, which is known to be NP complete. The reduction involves constructing a voting instance from a 3 SAT formula, where each clause corresponds to a voter and each literal corresponds to a candidate. The authors demonstrate that committee W satisfies junior if and only if the 3 SAT formula is satisfiable. This proof relies on the concept of approval profiles and plausible approval sets. An approval profile is a collection of approval sets, one for each voter, and a plausible approval set is a set of candidates that a voter may approve. The authors show that if a satisfying assignment exists for the 3 SAT formula, then there exists a plausible approval profile in which no 2 voters approve the same candidate. Conversely, if a plausible approval profile exists in which no 2 voters approve the same candidate, then a satisfying assignment can be constructed for the 3 SAT formula. To illustrate this reduction, the authors provide an example using a 3 SAT formula with 4 clauses and 4 variables. They construct a voting instance with 4 voters and 3 types of candidates, demonstrating how approval profiles and plausible approval sets are constructed. The authors also examine the problem of necessary junior, which involves deciding whether a given committee W satisfies junior with probability 1. This problem is trivially in P for the joint probability model and the candidate probability model. For the lottery model, the authors provide a polynomial time solvable algorithm involving the definition of a set of voters who are not represented in W under at least one of their plausible approval sets. They check whether any candidate in C, W is approved by K or more voters in this set. The authors use specific notation, including I for the set of plausible approval profiles, A for a plausible approval profile, V** operator for the set of voters who are not represented in W under at least one of their plausible approval sets, senior for the set of plausible approval sets for voter I, and C for the number of plausible approval sets for voter I. The set of candidates not in W is denoted as C, W. The authors build on their previous work on the junior property and its relationship to voting systems, using established notation and terminology to describe the reduction and the proof. While the problem of necessary junior is trivially in P for some voting models, its complexity remains open for other models. Future work could involve exploring the complexity of the junior problem for other voting models. In approval-based committee voting, the justified representation, junior, problem involves selecting a committee that accurately reflects the preferences of voters. The candidate probability model, where each voter has a probability distribution over candidates, is a crucial framework for analyzing this problem. The authors investigate the complexity of deciding whether a committee can be chosen that satisfies junior with probability 1, denoted as exists nec JR. They introduce the concept of size JR, which involves finding a committee of size at most k that satisfies junior. By reducing it from the candidate cover problem, a variation of the set cover problem, they prove that size JR is NP complete. This result has significant implications, as it demonstrates the computational intractability of determining whether a committee can be selected that always satisfies Junior. In the candidate probability model, the authors establish a crucial equivalence. A committee W satisfies Junior with probability 1 if and only if W equals the set of all candidates and the committee size K is equal to the number of candidates. This result is derived through a series of lemmas and theorems, including a reduction from size JR to exists nec JR. The paper's main finding is that the exists nec JR problem under the candidate probability model is NP-complete, implying that it is computationally intractable to determine whether a committee can be selected that always satisfies Junior. This contribution advances our understanding of the complexity of approval-based committee voting and its implications for fair representation in collective decision-making processes. In this section, the authors demonstrate the NP-completeness of the exists nec JR problem under the 3 VA models through a reduction from the size JR problem. This reduction involves constructing a new instance I, from an instance I of size JR, where each voter I in V plus disapproves of all candidates in C and finds all new candidates possibly acceptable. The committee size K is set to 2K, and the reduction can be done in polynomial time. The authors show that every yes instance of I is a yes instance of I, and vice versa. If I is a yes instance of size JR, then there exists a committee W that satisfies Junior in I by constructing W equals W union C plus. It satisfies Junior under all plausible approval profiles of I. Conversely, if I is a yes instance of exists nec JR, then there exists a committee W that satisfies Junior under all plausible approval profiles of I. By removing C plus from W, the authors obtain a committee W that satisfies Junior in I. The authors extend this result to show that exists nec JR is NP-complete for the lottery model and joint probability model. The instance reductions for these models involve similar constructions as in the 3 VA models, with modifications to the approval profiles and probability distributions. The reductions can be done in polynomial time, and the authors argue that every yes instance of I is a yes instance of I, and vice versa. The main result of this section is Corollary 1, which states that exists nec JR is NP-complete for the 3 VA models. Theorem 4 further extends this result to the lottery model and joint probability model. These results demonstrate the computational hardness of the exists nec JR problem under various approval-based committee voting models. The exists nec JR problem is proven to be NP-complete under the joint probability model, even when restricted to only 2 approval profiles with positive probabilities. This is achieved through a reduction from the size JR problem, which is known to be NP-complete. By creating a new instance of exists nec JR with 2 approval profiles and constructing a committee that satisfies the justified representation property under both profiles, the authors demonstrate that every yes instance of size JR corresponds to a yes instance of exists nec JR, and vice versa. In contrast, the authors prove that exists nec JR is in P under the lottery model, when each voter approves of only one candidate in each plausible approval profile. This is achieved by counting the number of voters who potentially approve each candidate and selecting a committee that contains all candidates with a count greater than or equal to n, k, where n is the number of voters and k is the committee size. This committee is guaranteed to satisfy the justified representation property with probability 1. These results provide novel insights into the computational complexity of the exists nec JR problem under different probabilistic models, highlighting the challenges of solving this problem under the joint probability model and the feasibility of efficient algorithms under the lottery model. The findings have significant implications for the design of efficient algorithms for solving the exists nec JR problem, and underscore the importance of considering the underlying probabilistic model when evaluating the complexity of this problem. The JR probability problem is a complex computational challenge that involves determining the probability of a given committee W satisfying the justified representation, Junior, property. This property ensures that the committee accurately represents the diverse preferences of the voters. The JR probability problem can be expressed mathematically as P W satisfies Junior equals underscore a element of A. Delta A times I is JR W. A where I is an indicator function that returns 1 when is JR, W, A, is a yes instance, and 0 otherwise. In the context of the joint probability model, which takes approval profiles and their corresponding probability distributions as input, Theorem 7 states that JR probability is in P. This means that there exists a polynomial time algorithm to solve this problem. However, the decision variant of JR probability, which involves assessing whether the junior probability of W exceeds a designated threshold tau, is n-fard for the lottery model. Specifically, when tau is set to 0, the problem transforms into is POS JR, which is NP complete, Theorem 1. Corollary 2 further states that JR probability is n-fard for the lottery model. Moreover, JR probability is P-complete for the 3VA model, and consequently for the candidate probability model. This result is proven by reducing from vertex covers, the problem of counting the number of vertex covers for a given graph, which is P-complete, lemma 3. Solving JR probability for the 3VA model involves counting the number of plausible approval profiles for which the given W satisfies junior. Theorem 8 states that JR probability is P-complete for the 3VA model. The proof involves reducing from is JR, the problem of counting the number of plausible approval profiles for which a given committee W satisfies junior. This reduction is done by constructing an instance I equals V, C, P underscore, I, C, K, W, of is JR from an instance I, equals G, V, E, of VC, such that there is a one-to-one correspondence between vertex covers and plausible approval profiles for which W satisfies junior. The reduction involves creating a voter per vertex, and for each edge, I, J, in E, creating a candidate C underscore, I, J, that is approved by voters I and J with probability 1, and disapproved by other voters. Additionally, a set of K equals N, 2 candidates C plus is created, and each voter approves of C plus 1 with probability 0.5. The committee W is set to C plus, and the reduction can be done in polynomial time. The authors establish a correspondence between vertex covers in the graph I, and plausible approval profiles in I that satisfy the justified representation, junior, axiom. This correspondence reveals that every vertex cover in I corresponds to a unique plausible approval profile in I for which the winning committee W satisfies junior, and vice versa. Given a subset of vertices S subset equal V, the authors define a plausible approval profile A underscore S, where voters in S approve of candidate C plus 1 and the remaining voters disapprove of C plus 1. They demonstrate that if S is a vertex cover, W satisfies junior with respect to A underscore S, and conversely, if S is not a vertex cover, W does not satisfy junior in A underscore S. The authors then present Theorem 9, which states that JR probability is in P for the 3VA model if pi, C element of 0, 1, for all I in V and C element of W. The proof involves defining a set of voters V, who have not approved any candidate in W and counting the number of plausible assignments of vote as unknown approvals under which W does not satisfy junior. The probability of W being junior is calculated by counting the number of plausible approval profiles and those that violate junior, and is expressed as the product of individual probabilities, where each term corresponds to 1 minus the probability of W violating junior because of each candidate J element of C, W. Furthermore, Theorem 10 states that in the 3VA model, counting the plausible approval profiles where W satisfies junior can be computed in polynomial time if K equals N. The proof involves showing that when K equals N, ensuring junior for a plausible approval profile requires that each voter who approves at least one candidate must have at least one of their approved candidates represented in the winning committee W. These results provide a significant contribution to the study of JR probability in the 3VA model, demonstrating that the problem can be solved in polynomial time under certain conditions. Computational complexity of approval-based committee voting under uncertainty is a critical aspect of voting systems. This section focuses on the complexity of problems such as exists nec JR, max JR, is nec EJR, is POS EJR, and exists nec EJR under different uncertainty models. To begin, We compute the count of plausible approval profiles where a given committee W satisfies the justified representation, junior, condition. This count, denoted as T, can be computed in polynomial time using the formula T equals underscore, a element of a P, W. A, where a P, W, is the set of all approval profiles that justify W. The overall number of plausible approval profiles is then obtained by taking the product of these individual counts. The authors establish the NP hardness of max JR for all four uncertainty models by reducing from the NP complete problem exists nec JR. This reduction involves constructing a new instance I, from a given instance I of exists nec JR, such that the maximum value of JR in I is equal to the number of justified representatives in I. This result has implications for the complexity of other problems in the paper. The section then shifts its focus to the computational complexity of problems related to the stronger concepts of proportional justified representation, PJR, and extended justified representation, EJR. The authors rely on the CONP completeness of is EJR and is PJR to establish the CONP completeness of isnec EJR, is POS EJR, isnec PJR, and is POS PJR for all four uncertainty models. Theorem 11 presents a proof of the CONP hardness of exists nec EJR for the candidate probability and 3VA models. This proof involves a reduction from the CONP complete problem is EJR. The reduction involves constructing a new instance I, from a given instance I of is EJR, where new voters and candidates are added to the original instance I. The approval sets of the original voters are preserved, while the new voters are designed to disapprove of certain candidates and find others possibly acceptable. This construction allows the authors to establish the CONP hardness of exists nec EJR. These results provide a comprehensive analysis of the computational complexity of various problems related to approval-based committee voting under uncertainty. The findings have implications for the design of efficient algorithms for these problems and highlight the challenges of dealing with uncertainty in voting systems. This research paper delves into the complexity of computing a committee that satisfies the extended justified representation, EJR, and proportional justified representation, PJR, axioms under various uncertainty models. The authors demonstrate that the problem of finding a committee with a probability of being EJR, resp. PJR, equal to 1, denoted as exists nec EJR, resp. Exists nec PJR, is conf-fard for the lottery and joint probability models. This result is achieved through a reduction from the is EJR problem, which is known to be n-fard. The reduction process involves constructing a new instance I, from the original instance I, where I includes new voters and candidates. The authors show that if I is a yes instance of is EJR, then I is a yes instance of exists nec EJR, and vice versa. The proof relies on the construction of a committee W that satisfies EJR for every possible approval profile, and the authors argue that W cannot include any candidate outside of C plus union W, where C plus is the set of new candidates. Furthermore, the authors establish that if I is a no instance of is EJR, then I is a no instance of exists nec EJR. This paper also establishes that the problem of computing a committee with the highest probability of satisfying EJR, resp. PJR, denoted as max EJR, resp. Max PJR, is conf-fard for all four uncertainty models, 3VA, candidate probability, lottery, and joint probability models. This result follows from the CONP hardness of exists nec EJR, resp. Exists nec PJR, as the latter problem reduces to max EJR, resp. Max PJR. The findings in this paper underscore the computational complexity of ensuring fair representation in the presence of uncertainty, providing new insights into the challenges of designing efficient algorithms for committee selection under various uncertainty models. Approval-based committee voting under uncertainty, a comprehensive analysis. This paper delves into the concept of approval-based committee voting in the context of uncertain preferences, providing a comprehensive analysis on how to make collective decisions when individual preferences are not well defined. The study aims to bridge the gap between social choice theory and real-world decision-making processes, where uncertainty is often an inherent factor. In approval-based voting systems, voters approve or reject candidates rather than ranking them. However, when voter preferences are uncertain, this can lead to inconsistencies and inefficiencies in the decision-making process. To address these issues, the authors develop a novel framework that integrates probabilistic models of voter preferences with approval-based voting rules. The paper's core contribution lies in its development of a new class of voting rules, dubbed probabilistic approval voting, PAV. PAV rules are designed to maximize the probability of electing the most preferred candidate according to the uncertain preferences of voters. These rules take into account both the probability distribution over possible preference profiles and the approval sets provided by voters. The authors demonstrate that PAV rules can significantly improve the efficiency and consistency of committee voting under uncertainty, outperforming traditional approval-based voting methods. They also show that PAV rules are more resistant to strategic manipulation, as they incentivize honest revelation of preferences even in the presence of uncertainty. Moreover, the paper explores the implications of PAV rules for various aspects of committee decision-making, including candidate selection, committee size, and the role of abstentions. It highlights the importance of considering uncertainty in voter preferences when designing voting systems, emphasizing that neglecting this aspect can result in suboptimal outcomes. In conclusion, this research offers a groundbreaking approach to approval-based committee voting under uncertainty, providing insights into how to enhance the efficiency and fairness of collective decision-making processes. By integrating probabilistic models of voter preferences with approval-based voting rules, the proposed PAV rules have the potential to revolutionize the way committees make decisions in the face of uncertain preferences. Counting colorings and independent sets in sparse graphs and hypergraphs is a complex problem, with significant implications for computational social choice. In this context, understanding preference restrictions is crucial. A graph or hypergraph is considered sparse if its degree is bounded by a constant. The problem of counting colorings and independent sets in such structures arises in various applications, including computer vision, machine learning, and network analysis. The paper focuses on the p-completeness of counting colorings and independent sets in sparse graphs and hypergraphs. Specifically, it addresses the problem of counting the number of proper colorings and independent sets in graphs with a bounded degree. The authors demonstrate that counting colorings and independent sets in sparse graphs and hypergraphs is p-complete, even when the degree is bounded by a constant. The paper employs a range of techniques, including reductions from p-complete problems, such as counting the number of satisfying assignments to a Boolean formula. The authors also utilize the concept of holographic reductions, which provide a framework for reducing counting problems to other counting problems. Furthermore, the paper leverages the notion of degree-bounded sparse graphs and hypergraphs, which allows for a more nuanced understanding of the complexity of counting colorings and independent sets. The results have significant implications for computational social choice, as they highlight the importance of understanding preference restrictions in this context. The paper also discusses the limitations of the current approach and identifies avenues for future research, including the study of counting problems in more general graph and hypergraph structures.